So once the scientists got to know that matter is made up of atoms and molecules, the immediate interest was to find out how much does that atom and molecule weigh. Okay, you can't just take an analytical balance and measure an atom or a molecule, one single atom or molecule, because they're too small. So because of that, they had to come up with a way as to how to measure their weight. Okay, so what happened was there was probably they could do this. They could have maybe taken a known number of atoms, weighed the sample, and divided it by the known number of atoms. But till then, they did not understand how to count the number of atoms. Okay, so that's when Avogadro's hypothesis comes in. Now, this topic was already dealt with in the previous video, but I'll go over it again right now. So, according to the hypothesis, equal volumes of different gases under similar conditions of temperature and pressure contain equal number of molecules. As now, first of all, when we spoke about solids, liquids, and gases, we got to know that the gases generally occupy the volume of the container. So let's assume we have two containers, okay, and we are filling them up with hydrogen and oxygen. So the volume of the gas of hydrogen is equal to the volume of gas of oxygen. So the volumes are equal. And here the conditions of temperature and pressure are going to be the same. So temperature and pressure in both these containers are the same. Okay, according to Avogadro, if these three conditions are present, then the number of molecules will be equal. So, there are equal number of molecules of hydrogen and oxygen. Now, when they weighed this, they found out that the ratio between the weight of hydrogen and oxygen was 1:16, which means oxygen is 16 times more heavier than hydrogen. And oxygen will exist as a molecule. So this is the oxygen molecule, which meant that one atom of hydrogen and an atom of oxygen, again the ratio of their weights was 1:16. And that's when they decided to use hydrogen as their standard. Okay, so when hydrogen was used as the standard, they figured out the masses of various elements. But the main issue with this was the fact that elements started showing fractional masses. So if it was fractional, then obviously it would be difficult for us to use them in various calculations. And then they decided they will move from using the hydrogen standard, they changed it to oxygen. But after a few years of understanding and pondering about it, they came down to using carbon-12 as the standard for measuring the atomic mass. So according to which the atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon taken as 12. So we're talking specifically about the carbon-12 isotope. So according to that, atomic mass equals to mass of an atom divided by 1/12 the mass of the carbon atom. That will give us the atomic mass, and this has the units AMU. So the units used over here is AMU. After that, you need to obviously understand what does this AMU mean. It's basically one atomic mass unit, and it is equal to 1/12 of the mass of an atom of carbon-12 isotope. So it's the 1/12 of the mass of an atom of carbon-12. Okay, so these are the two main definitions we will be learning about in atomic mass. Now, sorry. Okay, so it was found that atomic 1 AMU is equal to 1.66056 into 10 to the power minus 24 grams. Okay, so this is the value of one atomic mass unit. And if we want to derive the mass of hydrogen, okay, so by an indirect method, the mass of hydrogen was calculated to be 1.6736 into 10 to the power minus 24 grams. Now, to calculate the mass of hydrogen in atomic mass units, you have to divide 1.6736 into 10 to the power minus 24 grams divided by 1.66056 into 10 to the power minus 24 grams. So when this is simplified, the answer comes up to 1.008 AMU or atomic mass units. And this is how the masses of various elements were calculated. Oxygen was supposed to be 16 and yeah, so the atomic mass unit can also be referred to as just U. So, as we know, atoms tend to exist not... Okay, so wait. Let's go back to the definition of this. Here, if you notice, we are specifically written as the mass of carbon, which is taken as C12. The reason we consider this is because carbon just does not exist as only C12. It exists in various forms, and these forms are known as isotopes. So, isotopes of an element will have the same atomic number, but will have a different mass, atomic mass, and this is because the number of neutrons are different. You had probably learned about this in class 10. So to recap, let's take carbon. Okay, and carbon's atomic number is 6. Okay, atomic number of carbon is 6, which means in its nucleus, the number of protons are 6, the number of neutrons are 6, the number of electrons will also be 6. So in the first shell, it will have 2 electrons, and in the second shell, it will have 4 electrons, because of its valency is 4. Now, here the atomic mass is equal to the number of neutrons plus the number of protons. So, 6 plus 6 equals to 12. So, this is carbon 12 isotope. When the number of neutrons changes from 6 to 7, okay, 6 plus 7 is 13. So, this is the carbon 13 isotope. When the number of neutrons changes from 7 to 8, it becomes C14 isotope. So carbon has the ability to exist in various isotopes. Okay, an isotope has the same atomic number but a different atomic mass. So what happened was, before 1961, there were two standards which were being followed. One of the standards, there were few chemists. Okay, let's take for example the oxygen. Okay, they assigned the value of oxygen's mass as 16, and another set of chemists decided that the O816 isotope of oxygen has the mass of 16. So obviously this meant there was going to be some amount of difference, and that's when they realized instead of taking it as the atomic mass of an element, we had to take it as a average of all the isotopes which are present. And this is where we have the topic of average atomic mass. Okay, now let's take for example, again we're taking carbon only. Okay, so we're taking carbon 12 and carbon 13. Okay, now For me to calculate the average atomic mass, let's for example calculate the average. So it will be 12 plus 13 divided by 2, and that will give you approximately 12.5. Right, so I'm calculating the average mass. But if you look at your periodic table, the mass of carbon is only going to be 12. It's not 12.5. Now the reason this happens is because your carbon 12 has a different abundance compared to carbon 13. So the amount of carbon 12 is going to be different than that of carbon 13, and that's why we need to consider how abundant are the individual isotopes. So again we will be doing carbon only. Okay, so the isotopes of carbon, let's take 12. C12 has a relative abundance of 98 98.892%. Okay, and its mass is 12. Alright, next C13 has a relative abundance of 1.108, whose mass is 13.00335. Okay, and C14, whose relative abundance is 10 to the 2 into 10 to the power minus 10, and whose mass is 14.00317. Okay, now obviously when I told you that if we'd considered just C12 and C13 as their masses and then just calculated, the value was coming as 12.5, which is wrong. So what we here, let's take this. Okay, now let's assume we have 100 atoms of carbon, out of which the percentage 98.892 could be C12, 1.108 could be C13, and 2 into 10 to the power minus 10 could be C14. Now, mass of 100 atoms of carbon will be equal to 98.892 into 12 plus 1.108 into 13.00335 plus 2 into 10 to the power minus 10 into 14.00317. All we're doing here is we are multiplying the relative abundance into the mass. Okay, this into this. So this, after simplification, we will get it as 1200.1, and this will be in atomic mass units U. Now this is the mass of 100 atoms of carbon, which means we need for one atom of carbon, which will mean we have to divide it by 100. One atom will be equal to 1200.1 by 100. Okay, so this is 12.001 U. Now, the reason I showed it as two separate steps is because you tend to get confused if I would have just put a divided between these two by 100. Okay, for future reference, you can directly, if relative abundance is given, you can just divide it by 100. So you need to write you can write this equation and divide it by 100. That will give you the mass of one atom of that particular element. Right. The atomic mass of an element is the average relative mass of its atoms as compared with an atom of carbon taken as 12. So in relative atomic mass, we are going to be taking the relative abundance, multiplying it with the mass, dividing it by 100. Okay, so basically we are converting the relative abundance to give us the atomic mass. Now, the reason we are considering relative abundance is because you have the quantity of the various isotopes will vary. The percentage of it has to be considered when we are talking about mass. Now, there is another important thing we need to be talking about at this point is the gram atomic mass. Now, the gram atomic mass is just that the atomic mass of an element in grams. That's all. So, gram atomic mass is just the atomic mass of that element in grams. So, gram atomic mass of carbon will be 12.001 grams. That's all. Okay. Do not get confused because gram atomic mass and gram molecular mass are two very essential topics when we do stoichiometric calculation. So when we say gram atomic mass, we just mean that the atomic mass is taken in the units of grams. That's it. We're not talking about how heavy or what exactly the mass of that particular atom is. We are only saying that the atomic mass is taken in grams, and so you'll have 12.001 grams of carbon, 1.008 grams of hydrogen. That's it. So do not get confused. Now, next we will be starting with molecular mass. Okay, molecular mass. Basically, the molecular mass of a substance is the number of times the molecule of an of an element or a compound is heavier than 1 by 12th of the mass of carbon 12 isotope. So this is just, so in molecular mass, all we'll be doing is we will be adding the molecular masses of individual elements. Okay, so let's take the example of H2SO4. Okay, so H2SO4 has two atoms of hydrogen, one atom of sulfur, and four atoms of oxygen. Now, we will just have to add up the individual masses, which means the molecular mass of H2SO4 will be equal to 2 into atomic mass of hydrogen plus 1 into atomic mass of sulfur plus 4 into the atomic mass of oxygen. Now we know that the atomic mass of hydrogen is 1 and that of sulfur is 32, and these are all going to be in U. So that is the atomic mass unit. So 32 and oxygen is 16. And when all of this is simplified, you get the value of 98.0 U. So all you have to know is that for calculation of molecular mass, we will be adding the individual atomic masses. And because you have two atoms of hydrogen, 2 into the atomic mass of hydrogen. Sulfur, there's 1, so 1. And 4 atoms of oxygen, so 4 into the atomic mass of oxygen. Now, in your textbook, there also you have an example problem, and this is about glucose. So C6H12O6 is the formula of glucose, which means number of atoms of carbon is 6, number of atoms of hydrogen is 12, number of atoms of oxygen is 6. Now to calculate the molecular mass, six into the atomic mass of carbon plus, sorry, I'll just capitalize this so that it's clearer, plus 12 into the atomic mass of hydrogen plus 6 into the atomic mass of oxygen. Okay, so we are considering the individual atomic masses C6H12O6. So 6, 12 and 6. So atomic mass of carbon is 12, 12.011. Okay, plus hydrogen is 12 of 1.008. You can just write it as 1.0. I mean, it depends. So if you're asked to go up to 4 decimal points, then you have to write 1.008, or you can just write it as 1.0. For this case, we will be writing the whole thing. 1.008 plus 6 into atomic mass of oxygen, 16.00. Okay, so when you simplify this and when you multiply and then simplify, you will get the answer as 180.162 U. So here what we've done is we basically multiplied the number of atoms into its mass, and that's how we've calculated the molecular mass. Similar to the gram atomic mass, you have something called as gram molecular mass. Now this means the gram molecular mass would be the molecular mass of that element, or sorry, of that compound or molecule in grams. So gram molecular mass of C6H12O6 will be 180.162 grams. Gram molecular mass of H2O, water, would be H is 2, oxygen is 16, so 18 grams. That's it. So gram molecular mass is nothing but the molecular mass in grams. Gram atomic mass was the atomic mass in grams. Molecular mass is gram molecular mass is the molecular mass in grams. With this we finish atomic and molecular mass. Next we will be studying about a very important topic called as the mole concept. Do check it out.